Have any of you have any of you here heard about the problem about rotating arrays? Which is, if you would to rotate this array to the left by 1, you would move this 0 here, and then the rest would be shifted to the left. So if we wanted to move 2 elements, you would move these 2 at the end, and then 2, 3, 4 at the start, right? So if you were to be asked to make an algorithm for that, what would your first idea be? So anyone here wants to answer? Go. No? Okay. Okay, so I'm going to answer that instead so we can pick up the pace. So the Pythonic way of doing that would be to create 2 slices, and you split up the part you want to rotate on. That would be at 0, 1, then at 2, 3, 4. And then, of course, you put them at the slots that you wanted them to be in. So that's the answer, right? So my issue with this algorithm is that it has a slightly higher, or not the optimal, space complexity, which is we're making 2 extra slices instead of just rotating it on itself. And we can do that, right? And so let's try to look at that algorithm. And we can actually achieve the rotations by using 3 reverses. And if you've spent a little bit of time researching about reverses, you'd know that it's possible to do them in place. So what would these 3 reverses look like? So first, we can reverse the entire array, and then reverse the parts that we want to rotate on. So if we wanted to rotate 2, we would rotate 2 from the last, and then the remaining would be rotated on themselves as well. And then we ended up with the same rotated array, 2, 3, 4, 0, 1. Right? So that happened with 3 rotations. Again, if you wanted to see that in slow motion, we see that happening here, slower, much slower. So, whoa, 0, 1, and then 2, 3, 4. And of course, since these reversals are not intersecting each other, they can be commutative, which means you can reverse the parts first before reversing the entire array, and you would get the same rotation. So as much as I would like to stand here and talk to you about algorithms, that's not what I'm here to do. And I'm actually here to present to you a talk on the tool I was using to demonstrate that algorithm. Okay, so mathematical visualization Python using Manim by me. So about the speaker, me, I'm currently studying BS Computer Science, and that's pretty much everything you need to know about me relating to this talk. Well, not exactly. So back in my first year, I had this batchmate, we called her Madame, and she was struggling a bit with our curriculum, or like the math and the coding. So she approached me and asked me to help her, or tutor her with that. So we did that. We went on a Discord call, and I got my drawing tablet, and then I drew math, and then she listened. And then that eventually blew up to our batch getting together every week, like about 20 of us, and then sitting in a Discord call with me and sometimes other people discussing topics that we found easy for ourselves and not easy for each other, for other people. And what is important in that is to realize that it made me realize that I like educating people. And I feel like a lot of the reason why I do what I do is that I can share what I know. So now let's move on to Manim, or Mathematical Animation Engine. It's an animation engine by Grant Sanderson, or you might know him as 3 Blue 1 Brown. He has a YouTube channel where he does a lot of visualizations using this because, well, he wrote it. And there's 2 versions of Manim right now. There's Manim GL. That's the one that Sanderson uses. And it's much more tailored to his workflow. And we have Manim Community, which has way better documentation since it's just a fork of Manim, but maintained by the community. It's written in Python and GLSL. And it has Jupyter Notebook support, and it integrates well with other libraries such as NumPy and Matplotlib and Pandas and whatnot. So it's really just good to add to your repertoire if you're already using other visualization methods in Python. And importantly, it's open source. And a lot of things that are cool are open source. And this one is a fork, so of course it's open source. So there's a lot of applications you can use for it. There's a lot of applications you can use for it. And you can see it on his site, 3blue1brown.com. That would be calculus, linear algebra, and all that other stuff. And before we proceed, let's look at the code for what I was presenting earlier. I'm not going to be coding that much, but this is what it looks like. So here we have that we're just importing. I'm going to increase the size of that. Okay. So we see here that we have a class, and then we're inheriting from a scene, and then all of that is inside of a construct function. That's how you would create a scene in Manim. You would create a construct, and then everything inside would be just declarations inside of Manim. Once again, I mentioned that Manim has really good documentation, so you should check that out. And you would be referring to it a lot because, like many Python libraries, it's very object-oriented, so you need to know the documentation with regards to the objects you're using, since it's going to be highly nested with like inheritance. So here we see that to create a main circle that we're going to be copying a lot later, we start with declaring a circle object, and then we create it 5 times, we copy it 5 times, and then we add it into this V group or vector groups. And that's how we access many objects at the same time. And not gonna go too in depth with the code, but here, let's scroll down a bit. So we see here that when we're rendering, we write it inside the self.play, and then we have helper functions here for the animations we want to happen. So the write group there, which means it was writing the circles into our screen, and then we're copying the group circles, and then we're setting the fill to 0. That's how we achieve the outline or like the slots for the circles, and then Mike again, sorry. So here we index the left and right, we slice, and you might have noticed that this group is the V group, right? And we're just slicing over it because V groups themselves, you can actually just access them and index onto them, and you would get the sub-objects inside. And since they're objects, if you were to do anything to the elements of a slice, you would be influencing the original list as well, since objects, yeah, they're going to be references. So here, this is how you create text. It's still an object, and then you can move stuff to the screen using more functions. So that would be toEdge, up, and then up here is actually not just a direction, it's going to be a vector, and we're going to be seeing a lot of them here in self.play. So here in self.play, we have, instead of a helper function for animate or like animations like write, we have here left.animate. Remember, left is our index is our slice, and before we do our shift, which is moving the object, we have an animate call. So what it does is that our shift is animated for the play. So yeah, so instead of just instantly moving this left slice in like down 1.5 and then left 1.5, we animate into that. So yeah. And then down here and left again are vectors. So they're gonna be like tuple. The first two would be the x and the y. And if you remember from your linear algebra, vectors are gonna be consisting of direction and the magnitude. So you're gonna be getting the direction of that based on the fact that these vectors are gonna be relative to the origin of our graph, or like, yeah, Cartesian plane. And then if we were to point it to 0, 1, that would be pointing to up by 1. And if we're multiplying vectors, what we're doing there is we're increasing their magnitude, or yeah, we're modifying their magnitude, because if it's less than 1, it's gonna be way smaller. So that's how we move them. And then that's pretty much everything else. So yeah, again, we're just rotating the slices, and that's how we get what we wanted from that animation. So next. Now let's talk about updaters. Manim is not limited to statically defined animations. Say, if I wanted to animate a ball like dropping, I would have to plot all of the points of the ball traveling, like simulating the deceleration and then the bounces and the loss of energy due to friction. And I don't want to do that. So using updaters, we are able to create and update objects at runtime or dynamically. And that would be using math. So here, let's move here to our next showcase, which is here. And then, oops. Oh, this is the wrong one. Okay. So this is what I mentioned. We have a ball here, he's bouncing, bouncing, bouncing. And we have its velocity here on the side. We also have a number plane. So let's go over how this happens. So this is really cool. So here, we have our updater scene here. So we see that we're defining a velocity and an acceleration at the top. And then we have this helper function here, grav. We're not going to go over it right now. So let's go over here down. We have number plane. So yeah, we have a function for that. It's defining the number plane. And if you look at here in circle, there's an interesting syntax here. And if you're familiar, you read into Python syntax way more than you should, you would know that this would be the matrix multiplication operator, and it's just overloaded into whatever they're using it for. So we have here 250, that would be coordinates on the plane. But the issue with that is if you're drawing a coordinate and you're shifting it to the side, your coordinates and your plane wouldn't align with the coordinates of the screen itself. So if you wanted to render something at 250 of a number plane, you would have to figure out where 250 is on the screen. And that is what this operator does. It converts your coordinates here into points on the screen. So to find 250 on our plot, we first just access it with at, and then so number plane at 250. It's pretty readable. So we have your number pause. So it's a number that we're moving to the right, and then here, let's go here to this function add updater. So we see that we have a pattern here for callbacks, and we see here that lambda m dot set value minus v. So m here would be the position object, and then we see that we're setting its value to negative v. So, so it would reason that this function is getting called. It's louder. It would reason that this function is getting called every frame, and then it's setting its value to negative v. That means v is getting updated every frame as well. So there are some updaters that we want to run on every frame, like this one, because we want the accurate values for v. But there are also some updaters that we don't want to run like exactly for every frame. Example, if we had a velocity of 1 and we were to shift that ball 1 per frame, and when we had the machine who could run it at 60 frames per second, it would move at 60 per second. So that would be pretty fast, and it would just go off the graph immediately. So we want to influence it by some factor. And if you're familiar with game development, you should know what this is, and it is delta time. It's dt. So that's the extra optional argument there for our updater function, dt. So down here, we see that our velocity is just going to be multiplied, the acceleration multiplied by delta time. So let's wonder, what is delta time, and why does it matter in this case? So let's scroll down here. And yeah, that's pretty much all of what that animation does. So let's talk about more about delta time. So we have a visualization here. We don't need to look at the code for this one, but visualization for delta time. I mean, it's a talk about visualizations. You should figure that's going to be a lot of visualizations. So here. So if we have a standard vector here, we multiply it by some velocity. So say if this was the down vector, that would be 0, 1, and then 0. The last one is z, so that was for if you want to work with 3D. But we're not working with 3D right now. So 0, 1, and multiply it by some velocity. So that would be, if we had a velocity of 2, it would be scaling the distance by 2. And then this entire thing happens in one frame, 0, 1. But if we were to multiply it by this factor delta time is the inverse of your frames per second. And not inverse, reciprocal. It's the reciprocal of your frames per second. So if you had 15 frames per second, it would be 1 over 15. And then 60, it would be 1 over 60. You know how reciprocals work. And how would that look like? So instead of just one frame happening in 1 second, it's going to be split apart in all of your frames. So instead of happening in 1 second, it would happen in a spread inside of the 1 second. So it would happen. There would be 15 frames now inside of 1 second instead of 1 frame per 15 seconds. And this matters because if we have some continuous value such as velocity, if we were to multiply it with the reciprocal of our frames per second, that would make it consistent throughout all of these frames per seconds. And let's think about it this way: if we have 5 and if we wanted to make 5 happen over 1 second, we would have to divide it by our frames per second. So that would be 50 divided by 5 divided by 15, and then that distance travel is no longer span in 1 second, and it's spread apart. It's spread in a way that it can be animated well. So that's why delta time is important in updaters and also other things that require dynamic rendering and calculation. So takeaways. Everything is beautiful, and I know I have a friend. His name is Liam Mendoza, and he's a CS graduate, and he has told me that he no longer codes because there was not a lot of visuals in it, and that wasn't interesting and it's too stressful. And that made me a bit sad because there are things in coding that you can get that you don't really find anywhere else. And not just in coding, and just in learning and in science and mathematics, there are so many things that you can just miss because there are hurdles that you can't really pass. And that's not your fault because it's very easy to lose yourself in theory. That's why we need visualizations such as Manim and Matplotlib and all of the other things that exist. And part of being a better programmer is being a better educator. That's looking for tools to help you to help you increase your reach on who you can teach and what you can teach. And it's not enough to keep on learning for the sake of it. We should also learn for the sake of sharing it. And that would be all. Thank you. So, yeah, before I formally end my talk, I have a few people I would like to thank. I would like to thank Charmaine. She's been very supportive throughout the process, and then I would like to thank you, Arnold, for vouching for me a lot. And then my friends, my dad, my sister, who came from Manila and got me clothes. I'm a broke college student. I'm not high school anymore. I'm a broke college student, and I'd like to thank my tita Janice for funding all of that too. And yeah, thank you guys for listening. That was my talk.
Okay, sorry, lakas. Okay, thank you for that. Now it's time for the question and answer. Does anyone have any questions for our speaker? Okay, kindly step in here so that you can use the mic.
Hi, Tyrael. I don't know about you, but I have a question. Actually, I was really curious about your Manim, your use of Manim, and I was wondering how do you create a complex video similar to Three Blue One Brown? Like, do you create a function full of animation executions based on like one clip, or is it like one Python program for that one specific topic, and then what's your work? How do you have you done it so far? Like, what's your workflow about that?
There was the parts of the first visualization I showed that I glossed over it. It's adding sections. You can section your code in a way that you can like select which ones you can render, so your testing process is faster. So to answer that is, if I had a video, I would cut it up into sections. So in case I wanted to edit a part of it, like outside of Manim, I would have an easier way of doing it because the movie files are not gonna be in an entire clip. It's gonna be separated based on the sections that you set. So you can set a section for this, and then when you edit it in post, you can add a video like a B-roll, and then you can continue on a different part without manually splicing the clip yourself. Yeah.
So, need pa rin ang video editing.
I mean, yeah, if you wanted like a higher quality of video output, you would of course add in more. You would add in voiceovers, you'd add in like B-rolls and like chapters, and you can do all of that in Manim and then just put voiceover. But it would be a lot easier for most people to just add that in post with like an editing software. But for the visualizations part, yeah, it's really cool. You can do that.
Okay, does anyone have any other questions? Okay, feel free to step in here.
And hi, good afternoon. I'm Dan. I'm a data generalist, but my hobby is 3D graphics. So my questions is like two questions. One is, how different is Manim to Turtle, the native graphics of Python? And then second is that the use case I find in this is that if you're using Manim or Turtle for animations with Python, the only benefit is for deploying it on a web application or something that can be in real time, right, accessed. Because I also use Blender Python, so that and I see that the animation is actually easier to perform or to develop in Blender with Python as well. So what would be the other use case for using Manim over other graphic software?
Thank you for that question, Dan. So, for me personally, Manim, I don't see that much similarities with it with Turtle. Is that like the cursor that moves and then like leaves? Yeah, I don't see that much similarity in the sense that I feel Turtle is a bit more restrictive in what you can do and what you can draw, and more on what you can animate with that. And for Blender Python, I'm not personally experienced with it, but Manim, I don't really think its main goal is for deploying it as like a live feature for like a web application. I think it's more for like what Three Blue One Brown uses it for. It's going to be for content creation and like creating videos that you show to other people, like in like YouTube or other social medias. And yeah, I don't really think it's for exactly for web applications specifically. It's more for the video creating. Yeah, education purposes. Yeah.
Okay, does anyone have any questions? Okay, well, if assuming someone is still thinking of their question, I would like to ask something on my end too. If my assumptions are right, basically the endpoint of the Manim code is a video file, right? How long does it take to render typically a video? Let's say of a certain length, like around a minute, like Three Blue One Brown uses. And this is a little bit of a selfish request, but can you like show us a demonstration of it running and then the video output?
Can I have the HDMI? So most of the time, if you're going to be testing your animations, you wouldn't want to render them in their highest quality and their highest frames per second. So Manim actually provides an interface for that with its CLI. So you can render. So if you wanted to test your animations, you could render it at a lower quality first, and that would be 15 frames per second for ATP for ATP, and then the animation output I showed earlier was that was the ones I rendered already, and those were high quality. So it's kind of awkward. So yeah. So if I were to render this, I would just open this I would run something sa kung I would run it I would run it in my pipenv. sorry, that was force of habit. I would run it in my pipenv because I have this in a virtual environment. And the command would be preview, which is what opens it, and then QL, or for that's low quality, medium, high, and then I believe there's also 4K. So if you wanted to render it with low, you just do that, and then size at pi, and then it should do that rendering for you. So yeah, as you can see here, it actually uses cache data, so it can do it faster. But if we were to render it with a higher quality, of course, we would expect it to take much longer, which is why I already pre-rendered the stuff. So yeah. Oh, but this is not a good example because it's cached. But if it weren't cached, this would take a lot longer. So yeah, I hope that answers your question. So yeah, this one's rendering in 1920 by 1080 at 60 frames per second. But when I like run my tests, I render it at low quality. Yeah.
Okay, thank you for that. Nice Vim setup, by the way. Anyways, does anyone have any other questions? Okay, I saw someone from the back. Yeah, feel free to.
Hello. I just want to ask, since you're discussing mathematical visualizations in Manim, does Manim integrate LaTeX, like that document typesetting language? And how much of the LaTeX, let's say, libraries are well integrated, let's say? Because for some reason, I want to make animations about automatons, like the finite state machines, but I don't know how much I can do the animations in Manim.
Okay, another demo.
That was a really good question. So I'm gonna open the docs now because I said I didn't want to open it earlier because I would take up my time. But I'm not talking anymore. Like time, so I'm gonna open it. So here we have the mobjects reference, and we have here in text, and we have here what you actually wanted, which is for LaTeX objects. And we have here math text, and it supports like pretty much anything you would need for math because, well, it was made for mathematical visualizations, so it would have LaTeX in it. And I actually used a bit of LaTeX earlier for the visualization of the delta time. And yeah, so I think it's pretty well supported, if that was your question. I'm not exactly sure on the extent of it, but I believe it does take from your system na LaTeX. So if you have more plugins there, I think it should just get that.
Okay, we're not gonna remove the HDMI for now. Does anyone have any question? Okay, one last. I think we're open for two more. So, question, sir?
Kasi I also do TypeScript, and then I find this similar with Motion Canvas. Only difference is that Motion Canvas has a UI that you could use with the code, right? So I'm seeing this. Would there be a UI like Motion Canvas for Manim, since this is for Python? Right?
I am not aware of that currently. Yeah. So if you wanted to do something in Manim, that would be using the code. But it does have a lot of plugins, and you might find what you need there. It has plugins Manim community. And there's going to be a lot of stuff pre-built there in case you wanted a much more simpler workflow when it comes to stuff. If you wanted to do stuff with chess, you can do Manim chess, circuits, data structures, and stuff like that, fonts. Yeah. So to answer to your question, I don't believe there's a GUI implementation for Manim, but there are a lot of ways to make it as easy as if you had the GUI.
Okay, we're opening the floor for one last question. Does anyone have any other questions? Okay, going once, going... Okay, there we go. Oh, wait. I think we're open for one more. I don't know.
Yeah, hi. So you can call me Echo. Nice to meet you. Very informative talk, and I really appreciate it. My question is, Nanim is designed mostly for mathematical visualizations and simulations, right? So what would be, say, the use case of Manim compared to something like, say, Pygame, which is a wrapper around OpenSDL, right? So you're able to do things in Pygame that are much more low level than what Manim does. So I'm very curious, like, why not just use Pygame to animate stuff, right? So in the same sense, what does Manim give that makes it unique in its own right? Yeah, that's it for me. Thanks.
Okay, so my answer to that, wait, do I have to stand here so okay. My answer for that is, first I'm gonna start off with what Pygame has, which is it can do interactivity. So that's obvious because it's for games. And the difference maker there would be on the level of abstraction Manim provides over animation functions. It's if you wanted to animate something you do in Manim in Pygame, I would bet that there would be way more code to do, and you would have to, like you said, it was low level, so you have to write a lot of the tweening and the delta times and stuff. You would have to do that yourself. So I guess you could do the things you do in Manim with Pygame, but I believe there's a lot way too much abstraction in Manim compared to Pygame that would help you in your use case and in like the speed of your development and prototyping. Yeah.